Hello everyone, my name is Pradeep Loganathan, and in this video we're talking about securing the software supply chain. We're also looking at a demo of generating SBOMs or software bill of materials using a tool called Syft, and we'll also look at vulnerability scanning and vulnerability reporting using another tool called grype. The software supply chain is a pretty large vector of attack. It has various vulnerabilities that can be exploited to inject malicious code. The vulnerabilities can range from developers submitting bad code, either inadvertently or maliciously, which results in impacted source. The source control can be compromised, which would again result in your source being impacted. Source can be modified between your source control and your build platform, which would again result in your source being impacted. Your build platform can be compromised, which would result in your build artifacts being impacted. The package repository where your build updates packages can also be compromised, which would result in your distribution packages being impacted. The external package repository on which your internal builds depend on for packages can also be compromised. This would result in impacted packages, which would then be used by a build to create compromised builds. So in a lot of ways, your overall software supply chain is a prime target for a lot of malicious actors, and it needs to be secured. And the supply chain is under a lot more attacks. The number of attacks on the software supply chain has been consistently increasing, with a large number of them being reported. Uh, some of the famous supply chain attacks have been, for example, the 2017 Apache Struts 2 supply chain attack, wherein the Apache this particular library is used by Java-based web applications. It's an MVC library which provides a framework, which it provides an MVC framework for Java-based applications. The vulnerability within this package was reported. However, this vulnerability, once it was disclosed, was later used by attackers to compromise a bunch of systems. A patch was deployed, but unfortunately, because the supply chain systems are not sensitive enough to know and understand as to whether they're using the latest updated package, the compromised versions were continued to be deployed, resulting in a lot more systems being impacted. In fact, on March 7th, when this vulnerability was reported, and within a couple of days, the patch was applied. But even then, if you really look at it, almost a year later, even in March 2018, there were large systems such as India's Aadhaar being impacted by this particular vulnerability. Another pretty well-known attack was the event stream attack. The event stream is a JavaScript package. It's an NPM package, and this is primarily a package which has been in existence for quite some time. It initially appeared in 2011, where it was used extensively until 2015, where it sort of became it was not used as much as before. However, in 2018, I would say it was social engineering, wherein a new maintainer started to work on this particular package and introduced malicious code within this package. And once he introduced this malicious code within the event stream package, whenever anybody tried to update their package, it sort of brought in that malicious code into their systems. And again, the supply chain was not sophisticated enough to know and understand that this was an attack through the injection of malicious code through the whole package dependency. So we as developers need to also know and understand that every time we do an NPM update, every time we do use a Maven package or a Go package or a .NET package, we run the risk of introducing malicious code, or we run the risk of being inadvertent accomplices to an attack. Now, these supply chain attacks have been increasing over quite a period of time, and especially attacks on the supply chain have increased drastically in the last couple of years. The wider community has sort of organized itself and responded by a bunch of measures. One of these measures is the introduction of the SALSA framework. The SALSA framework stands for Supply Chain Levels for Software Artifacts. It's a security framework which secures from source to service. It's a supply chain security capability model which informs on how you can increase your supply chain security through a capability model with various capability levels defined within this framework. This framework has had large contributions from organizations such as VMware, Intel, Datadog, and many others. SALSA defines four primary control categories. The four control categories are source, build, provenance, and common. Within the source control category, there are various defensive measures in terms of making sure that the source is version controlled, that the source has a verified history, that source is retained indefinitely, and at least two people have reviewed this particular source. The build control category has various defensive measures, such as ensuring that the build is scripted, that the build can be deployed as build as code, that the build environment is ephemeral, and that the build can be reproduced. Within the provenance control category, there are various defensive measures in terms of making sure that provenance is available, provenance is authenticated, provenance is non-falsifiable, and provenance is service generated. The final control category is the common control category, where there are various defensive measures in terms of security, access, and super user access. In this, we'll in this further conversation, we'll start to take a look further at provenance. Provenance is the ability to prove more information about the software packages that we use to make sure that it is an authenticated package, and to make sure that the information that that particular package presents is non-falsifiable and that it's service generated. One of the ways of generating provenance is by using something called as an SBOM. An SBOM stands for a software bill of materials. An SBOM is an artifact which contains a comprehensive list of all package dependencies, files, licenses, and many other assets that together make a piece of software. Any software that we have has a bunch of packages within it. It has dependencies, there are licenses within each of those packages, files, etc. So an SBOM sort of brings it all together and gives you a list of all of those things within a package. For me, I generally tend to look at it as the ingredients list in any item that you buy in a store. So for example, let's assume you go and buy a pasta sauce in a store, and if you look at the bottle, you would have all the ingredients that the pasta sauce contains, so that you can be very sure if there is some things that you do not like or that do not go well with you, you can avoid it. So similarly, an SBOM lists all the ingredients within a particular software package. So what does an SBOM contain? An SBOM contains a list of all the software components within that piece of software. It lists all the versions of those components. It lists the various dependencies between all those components, including transitive dependencies. Transitive dependencies are when a particular dependency of a software component requires another dependency, which means a primary software component now has maybe 2 or 3 levels of software dependencies. So that's transitive dependencies. SBOM also lists all the licensing information. It also lists all the various OS packages. So for example, in case of a container, when you generate an SBOM for a container, it lists even the base OS packages. Now, SBOMs can be generated from a variety of sources. SBOMs can be generated from source code. You can point the SBOM generator tool at a directory which contains your source code, and it will generate an SBOM from all the information that it can glean from the source. SBOMs can be generated from application builds. You can point the SBOM generator tool at your build artifacts, and it will generate an SBOM to specify everything that your application build contains. SBOMs can be generated from container images. Container images have a lot of layers, and the application which is layered on top of it also has a lot of other dependencies. So the SBOM can, in fact, create a list of all of those catalog all of those packages. SBOMs can also be generated from running containers, and this is critical because when a container is running, it is very much possible that the layers within that container can be updated. It can change. New layers could be added. So SBOMs can be generated from running containers too. The various specifications in which an SBOM can be generated. There are three primary specifications, namely SPDX, Cyclone DX, and Software ID. SPDX stands for Software Package Data Exchange. The initial draft of SPDX was generated in 2010. It comes from the Linux Foundation, and the SPDX specification can be generated in various formats such as RDF, SPDX, YAML, or JSON. The other specification is Cyclone DX. Cyclone DX is a much recent specification. Its initial draft was generated in 2017. It comes from OWASP, and hence it's pretty heavily security focused. This specification can be generated in various formats such as XML and JSON. The software ID is another specification. It's a pretty older specification. Its initial draft was generated in 2009. It comes from the ISO IEC tech committees, and it can be generated in various formats such as XML or CBOR. SBOMs are used for compliance review, security assessment, license compliance, and integrity verification, and they are key to ensure the provenance of the software package that we are using. SBOMs is the first line of defense in preventing a variety of supply chain attacks. It provides provenance, which is key to understand what we are referencing or using. In fact, the US Executive Order 14028 now mandates that an SBOM should be provided for all software purchased by federal agencies, which means that generation of an SBOM is key and critical for any package that is used by US federal agencies. There are a variety of SBOM generators out there in the market. Some of the well-known ones are Syft and Turn. There are also SBOM generators right now available within Kubernetes and Docker too. As part of this demo, we'll also look at how we can use Syft as an SBOM generator. Okay. So the Syft installation is pretty simple. You can install Syft by downloading the executable into your bin directory, which I've already done over here. In this case, I'm using Syft to generate the SBOM for Nginx, and it's a simple matter of just running Syft against the Nginx image. And once I run it, the SBOM for Nginx, for the Nginx container, for the Nginx image has been generated. So it has 143 packages. These are the various packages within the Nginx image. And you also have the various versions that's been listed over here. It's a simple matter of generating the BOM for this particular image. You can also generate the BOM and output it as a JSON file. This would give you additional metadata, which is very useful. This is an example of the SBOM for Nginx, which has been output in the form of a JSON file. Another one that can also be done, I'll just stop this thing. You can also generate the BOM in cyclone.dx format, and you can output it to a particular file. So let's look at using the cyclone.dx specification to generate the BOM. Okay, so over here, I'm generating the SBOM in the cyclone.dx specification, and I'm saving it in this particular file. I will later see if I can use this file to do a vulnerability scan. So for example, over here, this file has been generated. So this file is in the cyclone.dx format, in the XML format. Basically, it's using the cyclone.dx specification in XML format. So let's then also look at we can also generate a BOM for a particular folder. As we discussed earlier, we can point Syft at a particular folder and generate an SBOM for that particular folder. In this case, I'm pointing Syft to my /opt folder, and over here it should be able to generate the necessary SBOM for packages contained within that particular folder. This is pretty useful. For example, if you want to generate SBOM for, let's assume, your source files. So for example, over here, this is the SBOM that it generated for all the packages in my /opt directory. I know that I do have Python libraries. I have the Azure AZ executables. There are a bunch of other packages over here. So it's been able to generate a lot of these packages that exist in my OPT directory as an example. Now, the SBOM generated by Syft can also be used by grype. So, for example, in this case, grype is a vulnerability scanner. We'll be looking at grype in the demo further as a vulnerability scanner. So I can use grype over here to scan the SBOM to report any vulnerabilities reported by that particular SBOM. So basically, Syft goes ahead and generates an SBOM, which we already did over here. We generated an SBOM and stored it in the .nginx in this particular file. And now what we are doing is to use grype to sort of review the software bill of materials generated earlier and see if there are any vulnerabilities being reported out of it. So if you can see over here, the SBOM that was generated out of Nginx image earlier is now being fed into grype, and grype is able to determine all the various vulnerabilities based on the SBOM that was previously generated. So this is how you can generate an SBOM, and also how you can use the SBOM for various aspects. For example, in this case, we use the SBOM being generated to be able to scan for vulnerabilities using grype. The SBOM generation can also be performed within a Kubernetes environment, which is what we basically want. So what we want to do is to be able to use the ability to generate SBOM through a whole CI/CD pipeline. And since CI/CD pipelines now run within a Kubernetes environment, we would like to have the ability to run the SBOM generation within our Kubernetes clusters. So what I've done over here is I've created a pod and I've used Syft within that particular pod, and I've asked it to generate an SBOM for Nginx as an example over here. So if I go ahead, let me just check if I have the right context. Yes, I'm pointing to the right context. So if I go ahead and apply this particular, and if I then get into this pod, Let's take a look at the logs for that particular pod. I'll just bring this up over here. So I have this pod running over here. So if I look at the logs for the pod, let me, and okay. Yep. So over here you can see that the SBOM was generated. You can see it's in the Syft and it does a similar output. So this is one way wherein you can generate SBOMs within a Kubernetes environment. So this is all about generating SBOMs. This is about the various formats of the SBOMs that can be generated. This is also about ensuring that you can run the SBOM generator in a Kubernetes cluster. We've also seen how to generate SBOMs for various outputs. For example, it could be against your source folder, it could be against your container image, etc. And we've also seen how we can feed the SBOM being generated into other tools. For example, we could feed the SBOM being generated into a vulnerability scanner such as grype in order to be able to scan for vulnerabilities. Now let us look at vulnerability scanning. So within the CI/CD pipeline right now, what we have done is we have ensured that we have a SBOM, and what is also happening right now is that you can also check for SBOM drift, wherein you generate SBOMs through all the various stages of your CI/CD pipeline. You could generate an SBOM when source is being checked in. You can generate an SBOM when you perform a build. You can generate an SBOM whenever the build is promoted. You can create SBOMs whenever you generate a container image. And then what would generally happen is that you would check for SBOM drift to make sure that only packages and software components that are that you know of and that have proven provenance exist within your software packages, and that nothing else gets added. So checking for SBOM drift is key to ensure that you are in control of the provenance of all your software components and you know and understand what exists within those software components. Now, the other part of this is also in terms of making sure that you can do vulnerability scans on the packages that you use. And there are tools out there to perform vulnerability scans. For example, grype is a tool that can be used to perform vulnerability scans. Let us run through in terms of making sure that we can install grype and sort of run through how grype works. Again, to install grype, you would use the grype executable and download it into your bin folder, which is what I've already done. Let me just check. Yes, I do have grype locally installed. So similar to what we did with Syft, grype can be used to run a vulnerability scan on container images, local folders, application output, etc. So in this case, grype did a vulnerability scan on an Nginx image, and it figured out that there are 143 packages and there were 151 vulnerabilities. So grype similarly generates an SBOM, and once it generates an SBOM, it uses its database of known vulnerabilities to make sure that it can identify vulnerabilities in the packages that it cataloged and sort of outputs all those vulnerabilities. For example, in this case, you can see that there are 151 vulnerabilities, with quite a few of them being high and critical vulnerabilities. Um, in fact, you can even scan an image on all its layers to report. For example, over here, you can see that the vulnerability database was updated. There are various sources for this vulnerability database, and grype always updates its vulnerability database before it performs a scan. In this case, what we have done is we have scanned all layers of the image and produced all the necessary vulnerabilities, or rather, we have reported all the vulnerabilities within that. Similarly, you can output vulnerabilities as a JSON, which would give you a lot more metadata about these vulnerabilities. So over here, I'm performing a vulnerability scan on the Nginx image, and I'm outputting it as JSON. I can then perform further matches using JQ. I can filter, I can sort of transform the output in a lot of ways. Over here, I'm just saying, hey, I'm just provide a list of CVEs that you found in this particular image. Similarly, I can do further filters in terms of outputting only fixed CVEs or CVEs which will not be fixed, etc. Or I can even say, hey, I mean, once you figure out that that there is a high CVE which is marked as high, you don't need to go through further scans, just fail through that. The other thing that we can also do is to ensure that we can update the grype database. It automatically performs an update whenever it runs, but you can also force an update. Now, all this is being run locally, but you can also run this within your Kubernetes cluster. Again, what I've done over here is to create a create a pod with the grype scanner, and I can apply this to my cluster. I can go, and this would be the grype pod. And if I let me expand this. Let me just check that I am in the right context. Yes, I'm in the Syft cluster, and this is in the Syft cluster. Yeah, and let us look at the logs for this pod. It takes some time for it to, because I'm running this on a kind cluster on my local machine. It is definitely a bit slow. So what's happening right now is it's pulling down the Nginx image, and it would generate the SBOM for the Nginx image. Then it would run a scan on the image and report the output. Uh, So this is what it is. So what we basically done is we have run the vulnerability scanner, and we have created a vulnerability report within a Kubernetes cluster. This is an example of securing your supply chain through various factors. We have seen two primary areas over here. There are a lot of other things that need to be done to secure your supply chain, but we're primarily focused on two areas. One is SBOM generation, and the other one is to do a vulnerability scan. And what we've also done is not only run these vulnerability scans and SBOM generation locally on our machine, but also run it within a Kubernetes cluster. In fact, there's a lot more that can be done. There are operators available, both for grype as well as for the SBOM generators. You can use these operators so that whenever any update happens to your cluster, scans can be run automatically without any additional work that needs to be done or any manual intervention necessary. And these operators would allow you to run these particular operators would allow you to ensure that you run both the Swift SBOM generation as well as the vulnerability scan whenever anything is updated within your cluster. And you can also put in admission policies to ensure that if a particular scan results in high levels of criticality or critical issues within critical CVEs, you can prevent a pod from being created. So this is an example of how you could use all these open source tools to further improve your security posture and to ensure that your supply chain can be secured. We have just scratched the surface with this demo. There's a lot more to it in order to secure a supply chain, but this would be a good start in terms of ensuring that you have an SBOM to prove provenance, and you can perform vulnerability scan and report on vulnerabilities. Thanks for watching. We'll be talking to you all soon. Bye.